Welcome back. This is lecture 8 of network modeling. As always, I need to remind you that the class is live streamed and recorded on YouTube. Today, we're going to hear from 2 more people in the class about their projects, and we're going to talk a little bit about antimony events, which we didn't cover last week. And I hope we can maybe get to doing a little bit more about motifs and phase diagrams. And so we'll start out, just review. Remember, we created this Google Doc where people can put questions. And Hayden, I guess you could reshare that in the chat if you're there for people. We'll do our best to see whether we can keep up with that and see what's confusing to people.
Yeah, I'll go grab the link.
And we tried running Antimony and Tellurium in Colab, and it had its quirks, but seemed to work pretty well. And so I have to say, I've been playing around with Colab, and people were going to look into distribution of packages on Colab. I know you can distribute through GitHub, for example, your Colab projects, or through Google as well. And then we also use this Antimony SBML translator, make SBML, and it worked well last week, and somehow it's been having problems this week. I sat down with Joel yesterday to use it to do some things, and typed some search terms into the chat, into the bar, and just got lost. So I think there's still a problem with the biomodels repository, and I'm not sure why it's not working well. I actually talked to the person in charge. I talked to 2 people in charge. I talked to the person who wrote this code, the make SBML models code. And remember last week, I think it was William, you had the problem where the translation was not running in Tellurium because there were illegal characters in the string. So they actually would like to have that documented, because they have checks that are supposed to catch that. And so if it's not getting caught and trapped, there's something going on with the code. And so actually the developer would like to know more about what happened. And I also talked to the people on biomodels, and they did in fact do a software update, and it broke the user interface. And they're working on trying to get it fixed. So at the moment, it may or may not work. You can certainly find things on biomodels, and then you can go and download from the original sources, but the biomodels repository download, it was not working as of today. And then we also talked about variable stoichiometry, and the syntax for that was pretty simple, with the exceptions that we had to be aware that we can't reuse symbol names. So if we have E plus N molecules of S, goes to ES, and ES goes back to E plus N molecules of S, we have to give the N's different names. And I think those are the main things I wanted to review. And I'd like to let Pedro and Ibrahim present their project ideas. Again, doesn't have to be very long or very detailed.
I found both models that worked and that didn't in the translator. And the most interesting one for gene regulation in innate immune response, was this one from Sato, where he tries to model the main known mechanisms in interferon regulation. And this is specific for Nipah virus, which involves antagonist proteins, and this apparently is not the case for influenza, which is my focus. Okay, this is a fairly big network, and it has so I studied it a little bit. So there is a positive loop on TNF alpha, positive loop on interferon, both interferons, alpha and beta, and also a positive feedback loop on STAT, which is something I didn't know about until I started studying. These are the antagonist proteins that negatively impact the innate immune response. This is what is interesting about Nipah virus. It disables in some it basically disables the ability of cells to defend themselves without the adaptive immunity. There is no viral replication. In other words, the virus that comes in it's not being released, so there's no arrow pointing in the virus. And NF kappa beta is included in the model as part of the viral sensor, this node right here, which promotes the interferons. Yeah, basically that's what it does here. And also the IRF7, which is the pathway, part of the pathway that promotes interferon again. So there are plenty of reinforced paths in this network. So what is interesting here, in my opinion, is that the interferon, which is released by the cell into the environment, is sensed back and promotes the production of more interferons. So this is an interesting feedback loop. It's like so the cell releases and senses what it released, which makes the cell release more. I found plenty of inconsistencies between the network and the equations they wrote. So, for example, virus produces interferon. There is no engagement of this specific path here. So TNFR, TNF alpha, they are not engaging in this equation. And also the interferon is being decaying, and this is not included in the network. And actually everything that decays here is not being explicitly written, drawn in the diagram, which is frustrating, but you know, we can handle at least the decays, we can handle it. But for example, this specific equation here, so TJ is this node here, TJ is this receptor, and I forgot what a star means. It's like activated. It goes back, so it inactivates, producing back the interferon that bounded to it, and gets back to the ground state, let's say. This is not being drawn here, so there is no backwards arrow of any kind. And what else? Yeah, so decays are not presented, and these PTPs and SOCs, they draw as they are inhibiting TYK2, but in the equations, this is written as decay of TJ, which is weird in my opinion, but okay. So I tried to look for other networks, like better networks, more consistent ones, and I couldn't find anything more interesting than this specific paper. So my decision was to stick with it and try to fix it and simplify in order to explore it fully and integrate with other models. So what I thought I was going to do, yeah, so there's no viral replication, there is no cell death. Yeah, that's it. So this is a simplified version from another paper, which basically grabs this network and writes it specifically for influenza infection. Much simpler, but again, all the same inconsistencies. Yeah, so I was comparing the equations. They have all the equations. This is good. All of them explained. And this is the model from, actually, I shouldn't be showing this. I should be showing the model that actually Alex is working on, which is a more population dynamics model. So you have target cells, eclipse cells, infected cells, and the virus. So let me get back here. So this is basically the network. You have the virus decaying, and it promotes in this setup, the virus promotes transition between target cells to eclipse cells. Eclipse cells are basically waiting the evolution of the infection. They are basically waiting to be infected, let's say, after the virus injected the RNA. So this is a virus is a promoter. In my opinion, virus should be part of the equation, but I don't actually know how to write this. So virus should be once a virus release the RNA inside the cell, the virus cannot do so to other cells. That specific virus is basically dead, I think. And then the RNA inside the cell creates more virus. So the cell in the infected stage releases virus and dies. And I tried to simplify as much as I could the interferon production inside the cell, and also trying to implement some kind of viral production inside the cell. So I will describe this ugly network that I drawn here because I couldn't do better. I'm sorry. So what's happening? So first you have the virus. The virus attaches to some protein in the cell membrane, which I'm calling sensor. So basically, that's this same network here. So there's a virus, there's a sensor, and it promotes the RNA that produces interferon. Okay, so the sensor promotes the interferon RNA. The RNA produces the interferon, and the interferon has this, in this case, small feedback loop through IRF7. So this is a feedback loop from the point of view of the interferon, and everything decays. So IRF decays, both RNAs decay, and the interferon decays. And the virus, it injects mRNA in the cell that produces virus and that releases virus. So this is as simple as I could do using RNAs, because that's my goal. It's to model the cell actively transitioning between the states that are in this small network here, the population model. So the cell would come from target cell to eclipse to infected and releasing virus, This is all being described by this network down here. And in some way, I would merge them together. I'm not sure how to do it, but the virus that was up there, now it is released by the cell. And the interferon could, for example, inhibit the transition between the target cells to eclipse cells, because the cells, when they sense a lot of interferon, they have a lot of interferon activity, they basically shut down the receptors to virus. That's what I've read in a paper. So it's like the cell closing doors and windows. I think that's ambitious, because I have basically no I don't have a solid background. I am simplifying the models. I don't know if this works. I know that the network above it, so the population model, works very well. And I'm not sure how I would merge them together. So this is my idea. I want to simulate the intracellular process of the cell producing and releasing interference as a response to the virus, and then merge it to either a population network, a dynamic population, or to a spatial model, like, for example, CompuCell. That's my idea, and I need suggestions, because I have no idea if I'm on the right track.
Okay, that's a lot of work. For the purpose of this class, I would recommend just doing the intracellular model. Take the one that you showed at the beginning and replicate it. You're trying to do something very interesting, which is merging a population model for cells with a subcellular model. The problem is that a population model for cells assumes that all cells of a given class are the same. And the moment you start modeling subcellular behavior, you're assuming that every cell is different. And so you're invoking an agent-based approach when you do that. And so it's a lot more straightforward to write the viral replication model by itself, the interferon model by itself, and then put them into cell agents in CompuCell or PhysiCell, and then have them interact that way. And so I think some of the issue here is that it's not totally impossible to do what you're trying to do, but it's not trivial to make that work. And I think already understanding that initial model that you showed, or a version of it, where you have the infection of the disease, infection by the virus, you have a sensor. Here they're using ERF7 is actually an actuator that's downstream of it's labeled just viral sensor, but those would typically be toll-like receptors. TLRs would be probably what they are. And as you point out, there's some positive feedback loops here that are quite interesting. You have the fact that you have this funny autocrine signaling, where the cell produces interferon alpha, but it doesn't respond to it inside the cell. It has to be secreted and then sensed on the outside of the cell, which is very typical of these interferon responses. And so I think just working with this model and understanding it is already quite a bit. And for the purpose of the class, if you can do that, you've done a lot. Now, there are lots and lots and lots of published versions of this model, which you might want to investigate. But for the purpose of this class, if you can replicate this model and the results in that paper, that would be enough. for this class. I understand for your research and going forward why you want to go beyond that. But to begin with, I would try to make sure that you understand this specific model. I'm trying to think if there's anything in this model that I'm looking at. As you point out, the arrows are not complete, the decays aren't written. This is what we were talking about, that not everything that you need is drawn in the diagrams to begin with. The one thing that you mentioned, which I heard that you might want to think about, is you mentioned that you said the SOCs and PTPs are inhibiting the tyrosine kinase 2 JAK complex. And you said they were doing that by enhancing degradation. And that's actually quite a common mechanism of inhibition in signaling networks. And I've mentioned it in passing a few times. In other words, typically we've had degradation just be K times the concentration. So we haven't had activated degradation or enhanced degradation. But it's not unusual to have the regulation of a concentration be done not by the production, but by the destruction. Because the amount of the molecule you have depends on how much you create and how much you destroy. So one way to produce more of it is to reduce the degradation, keep the production the same. One way to inhibit it is to keep the production the same and increase the rate of degradation. And that does happen. The star, in mathematics and physics, the star usually means a steady state. In biology, the star means the phosphorylated form of the molecule. And so a lot of these molecules, especially the kinases, will have an active and an inactive form. The active form is usually, although not always, the one with the phosphate attached to it. And the star indicates that the molecule has a phosphate attached to it. But I think this is a great project. This is I mean, we could sit down and go over the equations together, but this looks like a manageable level of complexity. As you point out, when you go from influenza to Nipah virus, the number of things that change is not so large. The main thing is your PV and W, which are the inhibitory molecules in the Nipah virus, are replaced by NS1, which is the main inhibitor of interferon signaling in influenza. And I think already, if you can understand the behavior of the circuit with those three feedback loops that you enunciated, you've done a lot. So I think it's a nice project, and there's a lot to learn from this model. And then if that's done and you want to go further, that's fine. But I encourage everyone to pick something that's achievable. Maybe it seems too simple. I mean, last week remember William showed something that he thought initially was pretty simple, but in fact there was a lot of richness to the model. And so I think don't be too ambitious to start with. I think this is already quite an interesting model. Great, Pedro. Thank you. Does anybody else have any other comments about this? This particular interferon pathway is pretty universal in viral infection. If it weren't there, we'd all have problems. And there's a specific problem that we have, which is that if you use a steroid inhaler, like beclomethasone for asthma or allergies, that inhibits this early interferon response. And so you're much more likely to get infected with influenza if you're using a steroid inhaler than if you're not, because of the suppression of this. This is actually a very powerful mechanism in antiviral response. It's essentially the second line of defense. Their barrier function which is the first line of defense, which is essentially keeping the virus from getting to the cells in the first place. The second line of defense is this rapid interferon response that leads to antiviral resistance in cells. And any virus that's going to actually infect us is going to have some way of suppressing this response. Because if this response works perfectly, then the virus will infect a few cells and not spread. And again, almost every virus you'll find will have some molecule that's a non-structural molecule that has the function of inhibiting some part of that pathway. And it's interesting that Nipah virus has so many different ways of shutting it down. Influenza focuses on one, but it's a great pathway to look at. And as Hayden says in his comments, once you have that core pathway diagram working, you can think about many ways of extending it and making it more detailed. But getting that base one to work, I think, is already quite a bit. For the purpose of this class, that's plenty. Okay, great. Ibrahim, did you have something you wanted to show us?
Okay, so hi everyone, my name is Ibrahim again. Just a reminder from, I guess, a few weeks ago, the presentation, kind of the topic that I'm interested in pursuing for this project is modeling predator-prey interactions. And just some background, I guess, just as a reminder. So predator-prey interactions are a pretty important field in ecology, and historically they've been simplified into a few basic simple models. But more recently, these simple models have kind of been expanded upon by adding different parameters and other constants to try and simulate other more nuanced features of predator-prey interactions. For example, like behavioral responses or behavioral modifications or other niche species behaviors. So the most, I guess, widely used and widely expanded upon model for predator-prey interactions is the Lotka-Volterra model. And basically, the Lotka-Volterra model is represented here, as we can see, is pretty simple. X is the prey population and Y is the predator population. And here we can basically just see that the change in prey population is dependent on alpha X. Alpha is just the intrinsic growth rate of the prey population, and beta is the effect of the predator's existence on the prey. So basically some positive value minus whatever the predator is, however much the predator is influencing the prey's decay. And then here, the change in the predator population is dependent on this delta XY. Delta is the influence of the prey's influence on the predator population, and then it's minus some, instead of intrinsic growth rate, it's intrinsic decay rate of the predators. So minus some decay rate. So basically the death rate of the predators. So this is the basic model. Kind of the paper that I was looking into was discussing different ways that this model has been expanded upon to become more diverse and more comprehensive. One of those ways is by implementing something called the fear effect. And typically in biological ecosystems, as I mentioned before, behavior is a very important characteristic that isn't necessarily directly accounted for by the Lotka-Volterra model. So this paper kind of wanted to expand upon adding a specific fear behavior. And the fear behavior kind of is the prey having some fear response to the predator, causing them to not directly be predated or behave in a way such that they can't directly be predated on. This kind of causes the predator to adapt to not, I guess, openly and directly prey or hunt the prey. So which kind of causes this short-term prey survival, but long-term predator success. Because the prey in the short term will hide, but in the long term, the predator will develop a strategy to circumvent the prey's timidness and be able to hunt, in fact, more effectively, because also the prey themselves are not as successful when they're fearful. So to implement this, they basically did some modifications on the Lotka-Volterra model. So we will ignore these two terms. These two terms are from another part of the paper that they were doing. They were discussing the alley effect. And the alley effect is related to the population density of both the predator and the prey. But basically, we are going to be looking at these terms. So specifically, the predator growth is related to its intrinsic growth rate times itself, and then also times this f of sy function. And this f of sy function is the fear equation, I guess it's as they call it. And the fear equation is basically any decaying function. In this case, they're using this function on the right of f of sy is equal to 1 over 1 plus sy. This is their decaying function, but theoretically, this could be replaced with another decaying function that one saw to be more representative of the fear in that specific ecosystem. So that's what this is. And then also this g of x times y gets replaced. So basically, it becomes a little bit more complex. And g of x is basically the functional response. And in the paper, they represented this with both a Halling type 1 curve and a Halling type 2 curve. And they kind of wanted to see basically how the effects of this fear factor in both Halling type 1 instances and Halling type 2. So here is some of the graphs they came up with. As we can see, they're actually quite similar to what we were doing in class. This is kind of just a parameter scan of S, and S is, if we remember from here, S is actually some fear constant. It's kind of indicative of the quantity of fear, I guess, or how impactful the fear is. But here they're just kind of just doing a parameter scan of the fear. And basically what they're recognizing is if the prey are more fearful, which is an S of 0.3, as we can see, the predator population or the prey population has that short-term success that I was mentioning before, but then a greater long-term failure, as in the predators have greater success in the future. But if the predator or the prey are less fearful, they kind of act in a typical Lotka-Volterra instance. So like I said before, it's kind of, we're kind of seeing the short-term success and then of the preys followed by after the predators adapt and recognize how to combat this fear behavior, the prey start to fail. And then here we have the plot of different values of the S parameter, and then also the steady state value of the population of the prey and the population of the predator. We kind of see that basically the more fearful they are, the less success both have in general. Although, as we can see in the top graph, respectively, the predators have more success than the prey. So here we're looking at some of the phase plots of different S values. Basically, they assign different parameters to try and identify instances where they could achieve either extinction of both species, extinction of just the predator species, extinction of just the prey species, or some harmonious coexistence in the system. And basically, I think we're going to go over phase plots today, so I don't know if it's important for me to go over how to read these, but just the gist of this is basically these lines kind of point towards if some initial conditions. So basically, the initial conditions of the predator and the prey will fall somewhere on this plot, and the gradient of these plot, which are these lines that we can see, kind of indicate the direction by which the prey and the predator populations will approach until they reach some sort of steady state. And in this case, with these parameters, they achieved extinction in both species, which is not good. Here, just the extinction of predator, here, just the extinction of prey, and here, which is probably the more interesting curve, which is the coexistence of both species, and this kind of proves that we can, in fact, model this type of fear-induced behavior with this, because it does produce a stable ecosystem if the parameters are tuned correctly.
Ibrahim, what are the numbers of the X and Y axis?
These?
Yeah, so
This is-
0.3 or whatever. Yeah. I mean, they're
These
not
are
always, yeah.
population numbers.
But what is, for example, a population of, because in the case B that was good, you would have 1.5 predator and 0.5 prey. I mean, is this?
So the steady state will be, or the equilibrium will be where this
Triangle is.
the triangle is, right? And
But
in
when
that
you-
scenario,
yeah. But
the
when you now
prey
go
population
to
is
figure
0.
7b that you said is most interesting, right?
Yes.
And then your triangle is by 0.3 prey. What does it mean? I mean, there is not a real prey. There's only 0.3.
You're right. So the 0.3 and the 0.1 are technically they're like initial values for predator and prey are kind of in this like non-realistic domain, which is like 0 to 1. But realistically, you could just put some coefficient in front of these and generate some realistic population. This is kind of like a ratio. So for every 1.5 predators, there's
Okay. I see.
0.3 prey.
Okay. Yeah. Thank you. Yeah.
Yeah. So here's just, so this is the inclusion of the fear. So basically some further developments of this project, as I mentioned before, are replacing the fear function with different decay functions and trying to figure out which of these decay functions, other decay functions kind of can, recreate some viable ecosystem. And also basically the additions to the logical Volterra model oftentimes are kind of these additions of like some constants, like we see, or not constants, but these like additional terms, which is this dx term and this ax squared term, which were added for the alley effects. So sometimes you can actually overlap or incorporate multiple of these. So like in this instance, they're including the alley effect and the fear effect. So also you can incorporate other, I guess, behavioral changes or other ecosystem factors like cannibalism or immigration that kind of have that similar type of change to the logical Volterra model. So you could overlap theoretically a bunch of different models to try and get some more developed, overarching, more thoroughly encompassing model, which I guess is my kind of plan for the project, is to select a bunch of these different models that affect the logical Volterra model and overlapping them to try and generate some more comprehensive model.
Can I
So
ask
here
more
are just the
question?
references. Sorry, go ahead.
You said about the holy type or something. holding type.
Oh, the Halling type. Yeah.
Can you explain a bit, because I've never heard this term before. Maybe it's just because of my mother tongue or so, but I don't know what this is.
Yeah, so these are just a more complex way, at least from what I understand, is some more complex way to I guess, if we look at the subtraction term in the initial Lotka-Volterra model, it's this BXY term, right? Or negative beta XY. Basically, you can replace beta X with this GX functional response, which is some more complex representation of that term, and that can be replaced by different Halling type curves. And one is XP, which is basically what we were looking at before, which is this beta X, right?
So your decay term is an own function that's kind of you.
Yeah.
Get you. Yeah. Thank you. Cool. Yeah.
No problem. That's, I guess, it. If there's any more questions.
No, I think this is good. I mean, I think maybe thing to do is to start implementing. I mean, if you could write a little program that plots the Lotka-Volterra results and plots the phase portrait, then you can gradually make the functional relations more complicated and see what happens. And so I think it's building up is a good way to start. Lotka-Volterra is what's called a linear model. The birth rates and the death rates are only proportional to the species populations. There are no nonlinearities. And because of that, it's very simple to analyze. Because of that, it also has some rather strange behaviors. It doesn't have any fixed points. It's neutrally stable everywhere. So very old. I mean, Lotka-Volterra long antedates computers. It's a very, very old model. And so in general, people don't use it in real world systems anymore. But it remains the sort of the basis for the simplest possible predator-prey model. And then everything else, as you point out, is an elaboration of that. Here on the screen right now, if you look at these two functional forms, G is essentially, looks like G is a predation rate here. And so in one case, the rate of predation is proportional to the number of prey and the number of predators. It's bilinear, it's linear in both. In the other one, as you point out, it's proportional to that, but divided by 1 plus QX, which means that as the number of X's go up, the predation efficiency goes down. And so those are two fundamental hypotheses. And you can make those hypotheses about everything. A lay effect addresses an observed paradox in ecosystems, which is that when the population of a particular species goes below some threshold, they go extinct, even if there's no predation. So what could be an example of why that could happen? Well, suppose you're polar bears and you are widely separated in space. And so if you're a polar bear and you want to find a mate, you have to go a long distance to find another polar bear. If the density of polar bears gets to be too low, you can spend your whole life looking for a mate. You never find one, you never reproduce. Normally, the simple assumption, which is in Lotka-Volterra, is that the rate of production of new individuals is proportional to the population. It's linear in the population. That gives you exponential growth. And then you have a saturation called the carrying capacity, which says if you have too many animals, they eat all the food and then they starve, so they can't reproduce. So there's a saturation. And that's what gives rise to the logistic equation. And that logistic equation, the other place you see that all the time is when you're doing cancer modeling. because cancer models have a lot of similarity with predator-prey models. But fundamentally, you say if the population is small, the rate of growth is proportional to the population. As the population gets bigger, you have saturated population where the population rate, the growth rate goes down again. And that's logistic equation. And in that case, the population will go up initially exponentially, and it'll saturate and reach a steady state. In the Allais effect, you say that for very small populations, the growth rate is less than you would expect. And in that case, you have a situation where if the population gets to be too small, it becomes extinct. And all of those things can be explored with this kind of analysis. And this could be very nice if you can plot those phase diagrams and maybe some bifurcation diagrams. You can give a user the ability to change a few parameters or to change the structure of the equations and see how things happen. So from a point of view of teaching about how these equations work, I think this is a great system. Okay. Any other comments or questions about project ideas? No. Okay, good. Well, thank you everybody for being willing to present today. I'm sorry that we lost some of the people in the class because Elmer wanted to do differentiation, and there was another student, Justin, had wanted to do differentiation, and you wanted to do predator-prey modeling, and then there was that Hattie wanted to do predator-prey modeling. And so in a sense, it's a pity that they didn't stick it out to partner up, because I think we could have had two very good teams that way. But that's where we are. Okay, so let's come back to the class. I just want to review, we talked last time about questions that we could ask about time series. And I introduced this classification of qualitative questions about time series, which primarily have to do with, do you reach a steady state? Do you have periodic oscillations, chaotic oscillations, or divergence? Semi-quantitative questions, is something increasing, decreasing, is something before or after something else? And then quantitative questions. When does something happen? How much of something do we have? How fast does something change? In experimental biology, usually quantitative questions are hard. And so most of the information we get is qualitative or semi-quantitative. And so we have to think about how to use semi-quantitative or qualitative question measurements to answer questions. And one of the things that we do most often is to create what are called phase diagrams, where we have a plot, for example, of two parameters in our system, and we do a map, which we say, for this set of parameter values, we see a steady state solution. And for this set of parameter values, we see oscillating solutions. And the borders between these domains of different behaviors, the boundaries themselves are called bifurcations. The borders between these domains may not be in exactly the right place in the model in the experimental system, but we hope that the general pattern of behavior, if we see the sequence steady state, oscillating, chaotic in the experiment and in the simulation, they should both be there in the same order. And so looking for domain boundaries or phase boundaries is a critical thing we can do with the simulations and with the experiment. So now I want to come back and do a little bit of, oh, sorry, William, go ahead.
Yeah, wait, with those graphs, you can't that's just sort of theoretical, right? You can't tell code to produce a phase diagram.
Well, how would we do that? You could think about how to do that. Suppose that you have a simulation.
Yeah.
And the simulation produces some time series. We could probably write an analysis that asks the question, do we get a steady state out of that simulation? Do we get oscillation? Do we get chaotic or divergent things? And we could scan in small increments the concentration of potassium and the concentration of sodium. We run the simulation 1,000 times. And for each pair of parameters, we check which one it is. We make a red dot, a blue dot if we're in steady state, a green dot if we're oscillating, and a red dot if we're divergent.
Okay.
And so we could build a model like this, a map like this. It might not, we might have to run a lot of replicas, and it might not be as pretty as this sketch, but we can do this in simulations. Just have to run the simulation a lot of times. And so we so far haven't done that, but it's something that we can do. If you do bifurcation diagrams in one parameter, effectively you're going across this line here. Say you say fix the sodium concentration and change the potassium concentration. Then you'd see steady state, oscillating, chaotic, divergent. We did a little bit of that at the end 2 weeks ago, where I showed that what the steady state values of one variable were as we changed parameters. This is essentially a two-dimensional version of that bifurcation diagram. So that's a good point. Other comments or questions about this? It's a very fundamental concept of a phase diagram. And if you've taken physics courses or chemistry courses, then you run into this concept quite a bit. If you haven't done physics or chemistry, then this could be might be an unfamiliar concept. And it does take a bit of getting used to think about how they work and how to calculate them. So I appreciate the question. Okay, so I want to go back and do some very simple coding today. And this is for antimony events. So one thing that we could do, suppose we want to imagine that at time X, we add drug Y to our simulation. Or at time X, we kill half of our cells. Or at time X, we add a virus to our simulation. Well, one way we could do this would be in the Python, we could do r.simulate up to the time where we add the virus. Then we could have the Python say add virus, r.virus plus equals something, and then run simulate some more. And so we can always do this sort of interventions into a simulation from Python. But one of the points of antimony is to try to have standard ways of describing these that aren't free code, that are more manageable from the point of view interpretability. And so if you do too much of that, you reinvent Python inside of your language, so you haven't gained anything. But some of these things can be simplified. And so here again, we're looking for what we call declarative model specification rather than procedural model specification. We'll come back to that in a minute. But antimony allows you within antimony to have discrete time events. And the syntax is quite simple. You have the option of naming the event. As usual, you don't actually have to name it, but it can be useful to have a name. So you say event name, colon, and then at, and then a logical expression, something that's either true or false, and then a colon, and then what you want to have happen if that logical expression is true. And usually we change a parameter or variable. And you can have multiple ones in the same line separated by commas. And so if we want to add, and maybe I should have not picked 15 units in the time of 15 because that makes it look ambiguous. At time 15, we want to add 15 units to the concentration of A. We'd say, here's rule E1. This is a rule now. E1 colon at time greater than 15 colon A equals A plus 15 semicolon. So that's pretty simple.
Is this now in every time step of the 15 minutes, or is this just one time?
That's a good point. This looks like it should keep adding 15 every time step. Yes, William, question.
Yeah, can you do this to change or add equations, rate laws?
So the answer to that is no, you cannot do that. But what you can do is have the rate laws predefined and set a constant, the rate constants to 0. And then you could turn them on at a given time. So if you set the rate of production of a molecule to 0, at time 15, you set the rate of production to not be 0. Then effectively you can turn on an equation that was pre-declared but not used. So to Elmer's point, I should be quite specific. The argument of the logical the argument after the at is what's called a trigger. And you've jumped ahead a little bit, but in fact, your insight that there's a problem here is exactly right. The way this works is that when the value of that logical expression goes from false to true, the action is taken once. So in this case, at time 15, when you go from 15 to 15.001, it happens once, and then it doesn't happen again. So that's how this works. Now, there was a bug in Antimony, or actually in Tellurium, that I don't know if it's fixed or not, which is if you have two events occur at exactly the same time, and they affect exactly the same variable, only one of them happens. So if I said E1 colon at time greater than 15, A equals A plus 15, and E1 colon at time greater than 15, A equals A minus 15, it would randomly add 15 or subtract 15 at time 15. If it worked properly, the change in A would be 0 because I'd add 15 and then subtract it. And so we can check, maybe we can check to see whether current version of Tellurium, which one works. I know the nanoHUB version, it will not work. If you do both at the same time, only one will execute. You can have two events that occur at the same time that affect different variables. There's no problem. It's only if they affect the same variable that there was an issue. And I think that's probably fixed now in the current version of Tellurium that's on Colab. Okay, so the first thing I'd like people to do is write a very simple simulation. You don't need to type the comments. We'll say we have a reaction A goes to B at a rate K1 times A. B goes to nothing at a rate K2 times B. Start out with 10 units of A and no units of B. And for Elmer, I have this comment x0 equals 0 that's left over from something else. It doesn't do anything. You don't need it. And then you can set K1 and K2 to some value you like. 1 and 2 is fine. Then at time 15, increase A. And why don't you first think about what this should do? What should the curves look like? and then maybe even on a piece of paper, sketch what you expect the curves to look like. And then try running the simulation. And what I'm going to do is I'm going to go around, I'm going to wait until somebody has it, and then I'll have somebody show it. And then when we've got that, we'll go forward. Ibrahim, question.
So does this event do it every instance where the time is greater than 15, or just once?
Well, that's a good question. That was the question Elmer asked. Why don't you
Yeah.
try it and see what happens?
I have a small question. This model and ends commands, what are they? I don't remember that we have used them so far.
At this point in the class, you should be able to build a model on your own. So if I show you sample code and it has something you don't need, don't use it.
Don't use, okay, good, yeah. Sure.
As it happens, for this particular purpose, you're allowed to name models within the code. So if you want to say that my model, just the way we can name a reaction, J0, if I want to say this model is called constant decay, I can do that. But I don't need to, it's not required. It happens that when I built this, I had templated in that way, but about half of the lines in this in the sample code are not things you need. So just write the simplest code that you can possibly do that will give you what you.
I'm getting a strange error.
Oh, you have an and without a declaration. That's what the problem is.
Okay. Do I even need the end?
No, you can't have the end. Basically, when you say when you build blocks of code, you have to have open and a close. So model then needs an and statement. So it's like a def for a function.
So yeah, so actually for this command here, I just want to quickly point out this, then you don't have to restart. It automatically puts the process and restarts, but you have to do this, and then after that you have to do shift enter, but you don't have to go here and restart the runtime. It's a bit easier. Then this is the model that I have, and then I put the model here, I load it, and I simulate it over 20 minutes or whatever the time is, and plot it. And of course, I expected to have a pulse in after 15 minutes, a one-time pulse as well, and it should go up 15 units, and that it does here. So it's around 1, and it goes up 15. And we have two different decay rates. So one was 0.2 and one was 1. So yeah, the model shows time course what I expected. Kind of.
Right. So I think the key thing here is the question that you and Ibrahim both asked, which is if you say at time greater than 15, does it keep adding 15 or does it do it once? And it does it once. So that's the key point here.
But I understood, as you said, that we could do something like this should now go to 30, but in 2 little time steps, kind of. Actually, no, it doesn't actually. Interesting. That's now a surprise to me, because I have to rename this A2.
Oh yes. So that's it. I should
That
have
would
said
choose 30, right?
if you name it, you have to give them different names. Yes.
Yeah. And now it complains.
Yeah, you're
let's see.
missing a column
Do I? Oh yeah, here. Yeah.
after the name.
They should go to 30 if I understood it right. And it doesn't. Interesting.
You can do I did time mod 15 equals 0. So it does it every 15 seconds. And it works for every 15 time intervals.
Sure.
Share my screen.
Yes, please. Yeah.
Okay.
I'm surprised that this now goes to 30, because in my opinion, it should be bigger than 15. It does the E1 once, but then it doesn't it forgets about D2 anyway. So what is then why we now can say equal? That's I don't understand. But anyhow, show your screen, please. Yeah, might I have to stop sharing?
Okay, yeah, okay. Wait 1 sec.
You've actually already done the next exercise, William.
Oh. Okay. Well,
That's fine. Let's see. You're ahead of me.
dude, this. Wait, I can't tell which one I'm gonna share. Yeah, that one. Yeah. I mean, I just thought like logically that would make sense and it works. So
Okay, that's great. Let me come back to this and as I say, you've actually done the next exercise. So yes, the concentration increases only once, triggers once. Okay. And in general, the trigger, the event will occur every time the trigger goes from false to true. So it's on the upswing of that. And I suggested you try sine of time greater than a half, but yours is your mod is probably a better way of doing it than mine. So why don't people try a sine of time or mod of time like Williams and see if you can get repeated triggering. So is it clear what to try? So if somebody want to try that. So everybody, Ibrahim and Pedro and Alex, were you able to get the basic simulation to work?
It keeps saying string object is not callable. Like, I try to use code that I know works from another phone.
Why don't you screen share it and let's take a look? Because I want to make sure everybody has the basic code working so that we can all work on this together. Otherwise,
So I was using code that I know works from another day, and it'll work for a little bit, and then it just stops. If I restart the runtime, this code will work. But then after like some amount of time, it won't work anymore. And this, like if I try that one, and then I'm not sure what's happening. As soon as I try to run this, nothing else will work.
well, so let's look at the one that's failing, the first one that's failing. Stop. If you jump around too much, it's hard to see. Okay. So scroll up so we can see the whole cell. Import Tellurium is TE, TR equals rate model.
You have to do an and in your code
Yeah,
when you
so
have a
the-
model.
not load A.
So the problem is that you have a syntax error here. And when the syntax error breaks Tellurium parser, it won't work for anything else. So if you get rid of the line model constant decay, it'll work.
Make it too literal.
I thought there's two equal signs on where it's dot load A. Is that not right? Is that right?
Oh, that's a good point.
So here, string object is not callable.
It's because your R equals TE. It's just oh no I say because somehow it takes this as a string. No, I didn't say anything, so I don't know.
Yeah, it looks like T. So scroll up, let's see the beginning of your code block, because this is strange. That's a little bit odd here. Okay. Oh, okay. So it may. I had some. So Elmer, I had some strange errors when I was using that kill function. That it worked sometimes and didn't work at others. So,
I don't know. So I mean, for me it works, but you implement 2 times Tellurium. So I don't know what the Q does. Install Q, but the U is updating Tellurium. So you install Tellurium and then you update Tellurium. You don't have to do it twice. One time is good enough, and then you don't have to do the opt install. You only do once. You do now everything twice. So opt and opt-get is old. You just need opt. You can this get is from, it stopped about to be used 3 years ago or so. So just get rid of the get in anyway. And 2 lines are just too much. Either you delete 2 lower lines or the 2 higher lines. Yeah. And the other thing is the same.
okay, so now let's see if the first one works.
I can go scroll down and see what is the
You
output.
see, it
from
says your
this.
session crashed for an unknown reason. I was getting, or is that actually correct? Because the kill is supposed.
Yes, the kill is killing the question, and that's why you not have to do it now. Now you just have to do the import. Now you have to use somebody to import it.
So don't
this
keep
one.
reinstalling it. You keep having cells that are doing the install again and again.
But what is now this going on? Yes, I think you have only to import your library. You have to import the library once, and you have to install your library, your C libraries with opt as well only once.
Oh, so I know what the problem is here. Look at your line with the it's a syntax error. You have a parenthesis, a closed parenthesis after a plus 15.
Oh,
There.
So who is now sharing the code? I don't know.
So Alex is
Alex. So Alex, just when you go to the first cell that you have, you do that everything that you have. So you need only 2 lines of this code. One opt installs you the C library libcurse5 that is used for Antimony. Then pip our Python library. So install the Python library Tellurium. And after that, because we only want to execute once, we import the OS, which is a standard Python library, and we use OS to kill. And from this, and this is a Linux command that kills processes. And OS get PID gives the ID from the current process that we at the moment running, and this is this notebook. And with 9 we say we just forcefully want to quit it. So we install the libcurse library, which is C libraries. We install our Tellurium package in Python. Then we load the operating systems library from Python, and we use the operating system library to kill our running process. And after that, when this is done, then you don't have to restart the runtime anymore, because these 2 commands do it. This import OS and OS kill. And then when you scroll down, now in the next code cell, you can write just your code, right? And whatever. And your code is only the browsing that you write. And then you load this code, and then you run the simulation, but you not have to import anymore, and you not have to do any more installation of C libraries. And so I think this messes up your code. So just in every line that you have there, in every code line, take this import Tellurium out. Otherwise, this is, I mean, it doesn't hurt here, but it's not needed, right? From the ID, and opt will really mess up.
Can you go to the previous cell? Yeah, this one. So go. No, that's you don't reinstall Tellurium. So get rid of that cell. No. Yeah. So the other day I said, when we started using Colab, is there a way to restart the kernel from inside of Colab? The answer is yes. So Elmer found that, and that's really a big help. Thank you. So okay, so now it should be. I think now it should be okay.
okay.
Anybody else? Everybody got it working now? Ibrahim, Pedro, is it okay?
Try doing the mod thing. For some reason it's not, well, it's doing something strange. Can I show?
Okay, let's see. So we can all help each other out. I mean, Elmer found something neat that was a really nice workaround.
So I'm doing just this time mod greater than 1.
Mhm.
And this is what you expect, right? But when I do 0, it just doesn't work.
You have to you have to set it equal to 0. Equal.
I tried this also, it didn't work.
So I have a question. Well, let's see. So greater than 0. Let's see, what was the one that didn't work? Okay, so which one worked?
If I do like any number other than 0, it works, but obviously offset by that number.
Right. Okay, so here, what is time percent 15? That's going to be a number between 0 and 15, right?
Correct.
Okay, so now you're saying setting it to 0
If I
doesn't.
set it to 0, nothing happens.
So this is always. Let's see.
Yeah, it's always true. No, let me see.
Oh, because when it's 0, it should be, so it should be false. So it shouldn't, when it's exactly 0, it should be false. And then it should at the next time step. Oh, I know what it is. Your time is not updating continuously. Your time is a float. It's not an integer.
Oh, true. Yeah.
And so time percent 15 is never going to be exactly 0. Because you're stepping continuously through time.
Do less than 1.
The 0.1 will work. Now you
It's skipping
notice,
one now.
okay, you missed one, but now why is that? Look at, now this is actually an interesting result. I had this also in my slide deck, but it's a little later in the class. What is your simulate doing?
It's
Tell me what the arguments of simulate do.
this is the starting, this is the ending, and this. Oh, you're saying that this isn't like fine enough.
Yeah. There you go.
Interesting. Okay.
Because you're only doing 2 time steps per unit.
Yeah.
So actually, if you want it to be, you could make it lined up. If you wanted to, you could make it 0, 50, and then 101 time steps. I think we'll do it correctly. Then it'll be lined up. But one thing you can always do is check. You can just print. Yeah, see, now it worked. Now 0 should work. I think you can try 0. Yeah.
Yeah.
So you can check this. Why don't you just print result after that? The first column is the time, so you can see what the times were.
Mm-hmm.
So 25, 27.5, 28, those were the times that were evaluated.
This would have. Okay, yeah, this makes sense.
But that's great. Those are the kind of things. Exploring these things is important, because sometimes we take for granted how these calculations are done, but sometimes it matters, the details. Great. Anyone else? Everybody got it? Great. Okay, so then the next assignment was basically to replace that one line with something that gave you a periodic signal. You could use the mod, or you could use something like sine, any periodic function of time. Did everybody get that? Do people need more time on that?
I think you're sharing the wrong screen.
Oops, what did I share? I shared nothing.
The New York Times.
That's not what I wanted to share. I didn't even know I had the New York Times open. I was looking at it before class. So, and I can't even see it because what I see is actually the Zoom session. So I can't even see what's on the page because I've got you guys in front. You guys are filling my screen. All right. At least it wasn't something very embarrassing. Okay. Okay. So back to the slideshow. Am I sharing the slideshow now? Okay, good. So is that coming back to what we had here? Has everybody got a periodic one, or does anybody need help with that? Okay. So the next one to do, yes, is this issue that again, triggering happens when the argument goes from false to true. And so if it goes true and then stays true, it only triggers once. So let's take that same simulation now and do something a little bit more interesting, which is instead of adding 15 to the value of A, make the sign of the reaction constant K1 go from K1 to minus K1. Okay. And think about what you think. Think about what you think will happen before you do it and see if it does what you expect. Okay, Pedro, let's see what you got.
It seems fine for me. I mean, if this is comment, okay, I think it is. At time above 15, K1 equals minus K1.
Okay.
Is it
About
okay?
the plot. Tell me about the plot.
Yeah, so the plot is completely wrong.
What do you mean by wrong?
Doesn't match my expectations.
Okay, why not? What did you expect?
I expect at least that A starts at 10.
Can anybody give Pedro a hint about what he's missing about his plot? Don't do anything. Let people look at it first. William, go ahead.
You set. Oh wait. Maybe no, I'm not sure. Well, it's just interesting. You do r3 dot simulate equals result, and then I guess that's fine. R3 dot plot. I think that's fine.
Let's get the same result.
No, I got something that I think should happen.
Okay, so I give you a hint. Pedro's code is working fine and it's plotting exactly what he has.
Oh, your time is what it should just go to like 15, I think. 0 to 15 for your simulate.
Well, before you do that, Pedro, look at the output. Tell me what.
Okay. So yeah, it's giving what I should expect. I for some reason I thought it was 1e minus 31. Yeah, so so now I understand what's going on. Okay.
You have an exponentially increasing function now.
Yes, sure.
It's blowing up. So
Mhm.
all you're seeing is that it blew up. Remember we said one of the outputs of a simulation can be time series can be it blows up in time. So, all right. Yeah. Does anybody else have something they want to show? Ibrahim, do you want to show us something?
So I just had a question. I mean, we can
Sure.
just do it based off what Pedro had shown also, but I was just wondering how we have negative concentrations.
So a negative concentration doesn't make sense in a chemical reaction. But we're forcing, if you look at the, Pedro, show the rate equations. If you have B going to A at a rate that's proportional to the concentration of A, then that reaction doesn't stop when the concentration of B goes to 0. And so we're forcing that when we force this reaction backward, we're doing something that's not physical.
Okay.
So it doesn't make sense. Basically, we're saying B is turning into A at a rate K1 times A. And that doesn't make sense because when we run out of B, it still continues to react. So we keep losing B. I'm not sure what you're doing, Pedro.
I am doing like activating the backwards properly. Like this.
Yeah, well, that would actually have a back reaction, yes. But it's still going to go negative because you're still it's not legitimate to have a negative rate constant in this situation.
But when B gets to 0, it should stop.
But when K1 is negative,
K1 is 0 now.
okay, well, I'm not sure. You're making K3 equal minus K1. I don't know. I don't have an intuition about what this will do. You could try playing with it. Tell us what you're trying to do and maybe we can understand.
Yeah, so the idea is we have this K1 times A. And then I want to flip to minus K1 times B.
Okay.
So to make the flip happen, I add the term K3 times B, but K3 is 0. At the moment when time is greater than 15, I set K3 to K1.
But
Oh,
you did,
that's what I have to do. K3 equals K1 without the minus sign. And then K1 is 0, and then it should work. Yeah, that's it. You invert what's happening here.
so this is a little bit like the question earlier about can you add equations to the system? And the answer is you have to type them out beforehand, but you could set the parameter to 0 and then change the parameter from 0 to something else and turn it on.
Yeah.
So that's possible.
Flags, using flags.
That's effectively what you're doing here. Yeah. Anybody else? These are great examples. I think that's it's good to explore. I mean, it's a simple concept, an event, but it's pretty powerful. And here's our example of that divergence that was something that we saw. Okay. We've triggered always on time, but any logical operation is allowed in an argument for an event. And so you could trigger off the value of a species. And of course, this happens. Something differentiates when the concentration of a growth factor goes above a threshold. A cell dies when the concentration of a toxin goes above or below some amount. And so you can trigger off of a variable as well as off of time. And so here I could say, suppose we want a direction of our reaction to reverse not at a fixed time, but when A gets to be less than 2. Then we type at A less than 2, K1 equals minus K1. Okay. So why don't you do that? Try that. modify your code so the direction of the reaction reverses whenever A is less than 2. Does anybody have a result for that? Pedro,
Yes.
what happened?
So when A reaches 2, it inverts the starts increasing again.
So something like what I have here?
Yes. Not the same rates, but similar, yes.
Yeah, people may have picked slightly different rate constants, different forms of equations.
Let me see.
I got the same thing.
You were running until 20. Let me see. No. No, it's not the same result. Like, double check. Oh,
We have
yeah, yeah,
different
yeah, yeah.
equations, different rate equations.
Yeah. Yes. Now I see.
Does anybody need more time with that? Everybody got that working?
Exactly the same now.
Mine is still not the same.
Okay. Do you want to show it, or is it reversing, or is it not reversing at all?
It's blowing up.
Okay, well, blowing up is normal for that. So let's do the last exercise, which is,
Ibrahim, I think your K1 is most probably 1 and your K2 is 0.2. So you flip them. That might be.
Yes.
Oh yeah, I
Happened
think that's
to
what
me.
the issue is.
so here's the last exercise, which is, suppose that you have the direction of K1 flip when A is less than 2, and now make it flip again when A is greater than 12. What happens? And this time Pedro can't answer. Let's have Ibrahim tell us what happened.
It looks like it. When we hit 12, I guess it kind of flips again.
You want to show us what it does?
When A hits 2, it flips, and then when it hits 12 again, it flips again.
So you've written a little bit of an oscillator, a funny kind of oscillator, because what's oscillating this is a purely declarative oscillator. It's a non-procedural oscillator. Biology doesn't have loops. It does have thresholds and levels, but it doesn't have loops. And so this is actually an implementation of a loop where there are no loops. It's a biologically natural way of having a loop.
What do you mean by loop?
Well, there are no for statements in biology. Because what in biology you have states, and they're things that happen depending on the current state of the system. That's all you have. And so there isn't the kind in general, you don't have the kind of memory that allows you to do iteration. So to me, this is because it's a biologically natural thing that is a little bit unexpected, perhaps. So you get this periodic oscillation. All right. So if you want to read more about events, I've said that Antimony won't handle delays, and it won't handle delays in the ODEs, in the rate equations, but you can have delays in the events. You can say trigger 10 seconds after the trigger, do something. I'm not going to cover those kind of delays here, but if you're interested, the documentation goes into some of the other features. So I wanted to talk a little bit about something that we did in actually the other day when we were talking about the variable stoichiometry, but I wanted to go over that in a slightly more formal way. So we can make rate constants change in time by declaring their functional forms, or we could actually define ordinary differential equations directly in Antimony. We could do both things. So suppose that our K1, our rate K1, was modulated by a time-varying sinusoidal signal, like K1 is equal to 0.2 plus sine of t. Now, that's not probably very realistic biologically, but something we can do mathematically. And boy, I realize I lost a slide here. So the syntax to make the variable modulated in time is that you have to replace equal sign with colon equals. And so I'd like people to try doing that. So instead of saying K1 equals 0.2, you have to use the syntax K1 colon equals, and then the thing that you want to have change in time. And I apologize for losing the slide. That I haven't done that. I think this may be it's inevitable during a course that will happen once in a while, but I don't think I've done it so far this semester. So I had moved these slides. These slides were initially in a different place in the lecture, and I reorganized them, and I lost the slide that defines the colon equal syntax. But is it clear what to try? So you'll take K1 equals 0.2, you'll replace the equal sign by colon equals, and then you want to make the 0.2 into a sinusoidally varying function. Try that out.
I get negative concentrations of B.
Yes, that can happen. If you want to show it, that can happen here, because if the rate constants go negative, it's not guaranteed that the values stay positive.
Yeah, I think that makes sense. Yeah. Should I share it?
Okay, that looks fine to me. Yes.
Did you say do K1 or K2?
I suggested K1, but you're free to. This is not an exercise where we're modeling anything biologically meaningful. It's just an exercise to learn how to use the colon equals function. So if you want to change K2 instead of K1, that's okay.
Okay, I did K2 accidentally, and it just modifies the A instead of the B, which makes sense because, or just modifies B instead of and no A, which makes sense.
So here I made K1 colon equals 0.2 plus sine of time. And as you noticed for this K1 will go negative, and so the value of A can go and B can go negative. So that was my example. It's not the most exciting thing in the world, but it's useful to know how to do that. What if you made K1 equal to 0.2 plus 0.1 times T? Try that one. Somebody want to show us what you got? Alex, do you have it? It doesn't do anything very dramatic, does it? The rate at which A is turned into B increases in time. So the slope of that curve will get steeper, but you don't see a lot. I don't think that's not a very exciting result, but it's definitely something that happens. And actually, this one is specifically, William, in the example that you showed in your potential project last week, where the damage went up and then came down again, and the damage level was controlling a rate. That's one way you could do that. You could implement it that way in Antimony. So that's what happens here. So one thing that we've done quite a bit is we've said K1 equals 1. We could say K2 equals 3 times K1. That would work. Now, one thing that's a little unusual in a declarative language is that the order of execution doesn't matter for most lines. And so if I set K2 equals 3 times K1, the regular equal signs are only evaluated when the antimony string is parsed, when you do your load A. And so if I set, say, K2 equals to 3 times K1, and suppose K1 is initially 1, and I now say K2 equals 3 times K1, then the value of K2 will be 3. If I now go in Python and change the value of K1 to be 2, the value of K2 does not change. And that's a bit inconvenient, because if we have a whole stack of things that we want to scale, suppose we have a scale factor, S, and we want to change a bunch of parameters to be S times 3, S times 5, S times 7, we now change the value of S in Python to do a parameter scan. It won't change the values. And so that colon equals forces the update when we change the value from Python. The other thing that I wanted to talk about is, and I had a whole bunch of exercises that go into that in more detail, but they're not really very exciting. I'll just say that it's easy to make mistakes. If you have a lot of parameters that are multiples of each other, and you change one of them by hand, and you expect the other ones to change and register with it, that doesn't happen. You have to use the colon equal syntax. Now, one of the things that Antimony does is designed to do is it's designed to express chemical reactions. Now, those chemical reactions turn into rate laws. And certainly if we write nothing goes to B at a rate semicolon K2 times B, that's equivalent to writing dB by dt equals K2 times B. So the arrow notation can effectively write ODEs if we like. We can also use the syntax directly, K2 prime equals 3 times K1, and that's equivalent to writing dK2 dt equals 3 times K1. We could equally well have written arrow, nothing goes to K2 semicolon 3 times K1, gives exactly the same result. So why don't people try using that syntax? So you could use the example we have here, and now make K2 ODE. So now K2 is now going to change by declaring K2 prime equals 3 times K1. Okay. Why don't people try that and see what it does? We've seen in a lot of papers, they don't use this rate law notation. They'll write the ODs explicitly for everything. And I personally prefer the reaction rate formalism because you can convert the chemical reaction forms into ODEs uniquely, but you can't go back from the ODEs to an underlying chemical reactions uniquely. And so there's more information in the arrow diagrams than there is in the ODEs. So literally here, you just have to add one line to your code, K2 prime equals 3 times K1. Does somebody want to tell me what they got when they did that?
It's graphing K2 because it's
Right.
changing, which makes sense.
Good. So you answered my next question exactly, which is why do you have the extra line, which is K2? And you
Yeah.
answered it, which is it's plotting it because it's changing. And so if you're going to use that notation and you don't want it to plot, then you have to use the column selection. You'll have to use that column selection option that we went over before to tell it not to output K2. So we could say time A and B, and then we wouldn't get blocked by K2. So now I'd like to come back to something more biological. We spent a fair amount of time today on projects, which is good. We spent some time on syntax, finishing up. I think basically we now have all the antimony syntax we need. There's plenty of additional antimony syntax. There are all sorts of things you can do with annotations, compartments, and other things. And I certainly don't discourage you from learning how to do those things, but we don't need them for the basic things that we're doing here, and at least not now. And that online manual and the textbook go into the details about how to do those things. The one thing that we still really do have to do will be stochastic simulations, because those are fundamentally different from what we've done so far. And that's actually also very easy in antimony. We simply replace the simulate command with Gillespie, which is the name of a particular approach to stochastic simulation. We don't change the declaration of our models, though, which is quite nice. But I want to come back to this question.
Actually, can I quickly ask, is this the same that they used for Mobos, this Gillespie stochastic simulation?
Well, MABOS is a Boolean network solver. So they're two, but yes, effectively you're in the ODE simulations, we use a fixed time step. A Gillespie algorithm asks the question, when is the next event? And so you have variable time step when you use Gillespie. And so
I hope we come back to that. So, and yeah, we will come back to that, right?
Herbert has a nice chapter on it, and we'll come
Okay.
back in a week or two. We'll come back and walk through that chapter together.
Okay, great.
I don't mean to derail it, but it's a fairly involved discussion.
Yeah. Okay, great. Yeah, I'm looking forward.
I don't have the slides. I don't have the slides today. So I wanted to come back to the Hill equation, and I think people were finding it not trivial to go from a diagram to differential equations. Although William walked us through last week an example of going from the arrow diagram to Hill equations as an example. So it is something that we do a lot. And Elmer found code that did it automatically, that basically ran the algorithm that I described verbally and just imposed that on the arrows. So we talked about, and it says last time, but now it's several weeks ago, the idea that we could have a Hill rate law, and the rate of product production is some Vmax times the activator concentration to the n divided by k to the n plus s to the n. That's the Hill structure. And it's convenient to divide through by k to express s in units of k. So we say s over k to the n, s over k to the n. In that case, basically this argument s over k to the n is a number that ranges a little bit awkwardly between 0 and 2 in that case, rather than 0 and 1. And so it's a little bit more convenient actually to have an extra factor of 2 and write these in the Hill function in the form x to the n over 0.5 to the n plus x to the n. In that case, x goes between 0 and 1. And there was a question earlier when Ibrahim was presenting the population models about why the ranges were essentially between 0 and 1 for the populations. In that case, you have a constant which is called the carrying capacity, which is also written by capital K, not accidentally, which is the population at which that population of organism is consuming all the resources in its environment. It's it's effectively the maximum stable population. And it's convenient to express the current population not as 4,536,000, but as a fraction of the carrying capacity. And in the same way with the Hill function, it's convenient to express things in terms of the ratio with either k times 2 or k, so that our value of our argument goes between 0 and 1. And then if we ask what's high, low, or moderate value of the reactant, it's always with respect to k. S over k is much bigger than 1. We're in the high concentration case. S over k much less than 1. We're in the low concentration case. S over k equals 1. We're always at half our maximum rate of reaction. Something that other people also maybe need to be clearer is that one of the things that I like about the Hill equation is that there is this nice symmetry where if we want to go from an increasing Hill function to decreasing Hill function, we look our Hill function as the form x to the n over k to the n plus x to the n. Here I've written k 1/2. And if I want to go from increasing to decreasing, I replace the x in the numerator by k. And so x to the n over 0.5 to the n plus x to the n goes to 0.5 to the n over 0.5 to the n plus x to the n. So the denominator doesn't change. The numerator goes from having the variable in it to having the k in it. And that makes it very convenient to switch back and forth between activating and inhibitory Hill functions. So I just want to remind people that there is this symmetry, because there was a homework problem that asked about this, and I think some people found that a little bit confusing. It just takes practice to get used to that. And then we talked about using Hill functions to translate signaling or regulatory networks into mathematics. And very often we'll see something like A promotes S. And we saw that today in the example that Pedro presented. And that is to be interpreted as, in this case, nothing goes to S, because A is a regulator, it's not used up. And that really means that nothing goes to S with a rate that's a Hill function of A. And if it's an activator, we use an increasing Hill function. If we have S1 going to S2 at a rate that's regulated by A, then we have to have some basic rule for how S1 would go to S2 without A being present. Here it could be V max times S1, that's just mass action, or it could be V max times S1 over Km plus S1, which is Michaelis-Menten, and in either case we multiply by that Hill function. Again, if we make all of our K's equal to the same value, 1/2, 1, 10, then we can combine all of these things and we know that the values are compatible with each other. That's why scaling out the Ks, if they're different in reality, is convenient. I'll skip the inhibitory one because I think that's clear from this. When we start out with a gene regulatory network, we have P1 promoting P2. We interpret that as P1 turns gene 1 on, produces P2. We have to remember that P2 will decay. And so this produces two chemical reactions. Nothing goes to P2. P2 decays. Our production has a basal rate of production, B1, our Hill function of P1, and we'll assume linear decay, first order decay. And so if I just see P1 goes to promotes P2, and I say it's a gene regulatory network, you can immediately write down the ODEs for it. Now, in some cases, you might assume that the decay isn't linear. There are other things that you can do, but the simplest form usually works. If it's inhibitory, the only difference is that instead of a P in the numerator of my Hill function, I have a K in the numerator of my Hill function. And so I recognize that it takes some practice to get used to this, but once you've done it for a couple of cases, it's completely automatic to do it. No, it's the same thing that you do again and again and again. Now, what becomes a little bit more complicated, and Herbert has basically a whole section of his other textbook on this, is when you have multiple signals that interact. So suppose that I have P1 and P2 controlling P3. In this case, I use the word "and" in two different ways, and I have to be clear about this. Suppose that P1 activates P3 and P2 also activates P3. Now, if I'm going to write a model of this, I have to have a hypothesis about how P1 and P2 interact with each other. I might have "and," in which case P3 is only produced if P1 is large and P2 is large. I might have an "or," in which P3 is produced if there's any P1 or if there's any P2. Or I could have some more complicated interaction. Unfortunately, maybe not unfortunately for biology, but unfortunately for people who want to write mathematical representations of biology, especially for gene regulatory networks, quite often you have quite a few signals coming into the same gene. Some of them may be activators, some of them may be inhibitors. And in reality, these simple approximations, and we saw this with what Elmer was talking about, where we had signals, where we had multiple signals coming in to control the same gene, and he was assuming either "and" or like interactions for all those signals. That's what we do because we have limited ability to understand, but the reality is more complicated. And in reality, we need to look at experiment and find out what is the interaction. However, typically we're going to assume the simplest thing, which is that most of our if we have two components coming in, we either have an "and," where we turn on if both of the inputs are high, and we're off if any of the inputs are low. Or we have an "or," in which case we turn on if any of the inputs are high, and we're off only if both inputs are low. Is that clear as a concept? And the mapping between real values for P1 and P2, that is continuous values for P1 and P2, and the Boolean network where the P1 and P2 are either 0 or 1, is not always obvious. And that's something that we have to play with a bit. And this is, I think, what Elmer really wants to explore, one of the things Elmer wants to explore in his project. So in a sense, I had not planned on actually showing these slides, Elmer. And then after last week, when you talked about Boolean networks, I decided I better put them back in. So people could either credit or blame Elmer for the fact that these are the slide deck today.
I think you give me credit, of course, right?
I'm teasing you. I'm sorry, I shouldn't tease. I need to do. I had the person who wrote CompuCell, Maciek, worked with me for more than 10 years as a senior scientist, and Maciek had a very dry sense of humor, and so he would say something, and people would look at him, and they would their mouths would be open because they couldn't believe somebody would say something like that. And so I told Maciek that he had to say every time he told a joke, at the end of the joke, he had to say, "This was a joke." Because with his tone of voice, nobody could tell when he was joking and when he was serious. So people thought everything he said was serious.
Well,
So
were the jokes, sorry, were the jokes just that bad that no one could know that they were a joke?
Well, sometimes, but it was more a question of tone. A lot of it is that we pick up that something is meant to be funny by the way we say it. I mean, not that we should go around saying, "I'm going to kill you," but if somebody says, "I'm going to kill you," in a flat tone, you run for the hills. If somebody is, "Oh, you did that again, I'm going to kill you," people will laugh. Maybe we shouldn't use terms like that, but still, there's some difference in tone. With Maciek, he must have been, I think he's a good poker player. You could never tell what the emotional content behind it was. And so I told him he had to say that was a joke, because people needed to know whether it was serious or not. Anyway, but I realize also if people have different language background, for instance, figuring out when something is a joke or not is hard. I know, famously people say Germans have no sense of humor because German jokes are funny for Germans, but often not funny for people from other cultural systems. There are traditions, there's culturally defined things of what's acceptable, what isn't, what's funny, what isn't. And they differ from society to society. I think that will get edited out of the video or transcript, but in any case, we can tell. Okay. So if we think about and or, and again, I've cut out some slides about Boolean networks. I had more slides on Boolean networks, probably because Elmer did such a good job introducing them. For an and system, and suppose we're going to always use that k equals 0.5 threshold. So basically, if our signal is less than a half, our switch is off or mostly off. If our signal is above a half, our signal is on or mostly on. So for an and, we want our output to be bigger than a half, if and only if x1 is bigger than a half and x2 is bigger than a half. In particular, if x1 is 1, then we should recover our Hill function of x2. If x1 is 1, basically x1 isn't doing anything, and we should just get a Hill function of x2. If x1 is 0, we should get 0 no matter what. So these are the continuous approximations to the Boolean gates. For an or, and winds up and is quite easy to implement. Or is a little trickier. For an or, we want our output to be bigger than a half if either x1 is bigger than a half or x2 is bigger than a half. If x1 is 0, we want our output to be the Hill function of x2. If x1 is 1, we always want to get 1, no matter what. And there are some biological examples of these. And Herbert in his enzyme kinetics books covers several of these. And is pretty easy because and as a logical operation is multiplication. And so, and in biology, this happens with situations where the transcription factor only binds if both A and B sites are occupied by the promoter. And that's pretty common. You need both signal A and signal B to turn the genome. And in this case, we can get our output that we want by simply multiplying the Hill function for signal 1 times the Hill function for signal 2. That will give us our desired output. If signal 1 is turned off, it doesn't matter what signal 2 does. If 1 is turned on fully, then 2 is our regular Hill function. And it always goes between 0 and 1. It never goes above 1 or below 0. For OR, it's a little bit more complicated. The problem is that OR corresponds logically to addition. But if we add two numbers between 0 and 1, we get a number that's between 0 and 2, not a number that's between 0 and 1 anymore. And so we have to think about slightly more complicated ways of combining things. And biologically, there are at least two forms. There are many, but there are two basic forms of cooperative binding. One is called competitive and one is called non-competitive. So a non-competitive binding would be, suppose that our gene is turned on by one site, but there are two molecules in the environment, either one of which could bind to that site. It's called competitive because there's only one target. So that's one mechanism that could give rise to this. Another one is that we have two sites, site A that binds molecule A, site B that binds molecule B. And if either one of them is bound, you transcribe. In that case, X1 and X2 behave independently of each other. In the first one, it behaves like there's just a signal, and the signal strength is the sum of X1 and X2. In the second one, X1 and X2 behave independently. Let's do the competitive case first. Here I have a single target, and I want to know what's the probability that either A or B is bound to the target. If I don't care whether it's A or B, this behaves as if the concentration were just the sum of A and B, in which case in my Hill function, instead of having just X1, I have X1 plus X2 divided by 0.5 to the n plus X1 plus X2 to the n. This has the appropriate value relationship. It's limited between 0 and 1. If one of them is 1, the other one behaves properly. You'll notice, however, that the switching point is now not K anymore. As we increase the concentration of X1, the half maximal value of X2 shifts to the left. And so we get a series of curves here. Here I'm basically doing a two-dimensional plot. X1 is on the x-axis, and I've done a series of different values of X2. And so the shape of my curve stays the same, but it gets shifted to the left. In non-competitive binding, I have to put X1 and X2 separately. So I have X1 to the n plus X2 to the n over 0.5 to the n plus X1 to the n plus X2 to the n. This also ranges between 0 and 1, which is what I wanted. It's also going to be always on when either X1 or X2 are turned on. But it has a bit of a different shape. It still has a maximum slope at a half. But in this case, instead of shifting the whole curve to have the same curve shape and shifting it to the left, everything's getting compressed and being pushed up as I turn one of the signals on. And so there are many other functional forms that I can use, but these are the two classic limiting cases. So OR and only has one fundamental representation in Hill functions, but OR has two fundamentally different representations that behave very differently. And so if you're going to convert from a Boolean network to the Hill function form, every time you see an OR, you have to decide which of these or something else you're going to use. Okay. If you have signals that are not scaled, you always have to rescale them by k before you put them in combination. Otherwise, it doesn't work. And so if we have values of P1 and P2, we need to divide them by 2 times K1, 2 times K2, and then we can combine them using Hill functions. And so I'm rushing a little bit because we're running out of time, and we can definitely come back to these. I strongly encourage people to look. There's a bit of this in our textbook, and that second textbook of Herbert's goes into a great deal of detail. The textbook by Oriel Lawn also goes into a lot of detail on this about combining signals. The reason I wanted to come back to this, and I'm not sure we're going to be able to come back to it today. Maybe we'll get started on it, but we won't be able to do all the exercises. Is that we talked about autocatalysis a couple of weeks ago. We said we have a signal A that promotes its own production. And then we used our rules, which was A promotes A, turns into nothing goes to A at a rate B plus max V max times A over K to the N plus A to the N. And then A decays to nothing at a linear rate. And you'll notice that here I have K1 and 10 instead of V max and 0.5. And the reason I have that is because Herbert likes to set his Ks to 10, not to a half, in his example problems. And he uses a different notation for the K. But this was already an interesting result, even with one molecular species, because it showed bistability. If our initial value of A was much less than 10, we got a low steady state value of A. If our initial value of A was much bigger than 10, we got a high steady state value of A. And so we had two steady states for the same parameters, but different initial conditions. And then we did a bifurcation analysis where we said, if we change the basal rate of production, what happens? If the basal rate of production is small, we have a high rate value and a low value. If we have a very high basal rate of production, then that dominates everything, and we only get the high value for our steady state. What about K2? Here, this is our decay rate. If our decay rate is very small, things blow up. Remember, if there's no decay, the values go to infinity. And so if our K2 is very small, we get divergence, but we only get a high value. If our K2 is very large, things decay very fast. If everything decays, we have nothing. And so if our K2 is very big, we get a steady state of 0 or near 0. But for an intermediate value of K2, we get both the high value and the low value. And the last one was K1, which was the rate of production of our chemical. If the rate of production is too low, we get nothing. If the rate of production is high enough, then we get a high value and a low value state. And so that in each one of these parameters, there are regimes in which we have two steady states, stable steady states, and regimes in which we only have one stable steady state. The value of k at which we jump, b equals 0.237. K2 equals 0.5, sorry, 0.05 or 0.13. Those are called bifurcations. So the last thing I want to do, and maybe people can start thinking about this problem. It was a homework problem, but let's think about it together. Was I wanted to come back to these problems that were in the homework that were a little bit more sophisticated, perhaps. In the homework, I gave you already the equations for them. But maybe now we can take a few minutes at the end of class and start thinking about what needs to be done to convert this diagram into rate equations. And the reason I needed to tell you about how to combine signals is here I have A promotes A. That was the thing we did before. That was the problem we just solved. Here I have A promotes B. That I also know how to write as a Hill function. But I have B inhibits A. And here I have two signals coming in. A is promoted by itself and it's inhibited by B. So there are two signals coming into A. And so I have to make a decision about how to combine those signals. And so what I would like people to do here, we're going to run out of time, but I would like you all on a piece of paper to start out and say, what's an arrow diagram for this? And then write a reasonable Hill function for dA by dt equals something, dB by dt equals something. And so I'd like people to take just a few minutes to do that. And when you're working with molecular pathways, generally we don't know the rate laws and the parameters. And so we have to do this by hand all the time. Is it clear what I would like you to do? You're going to write two equations, dA by dt equals something, dB by dt equals something. And they're going to be based on Hill functions of the kind we talked about, based on this diagram. And may I make a suggestion? My suggestion is write the equation for B first, because it's simpler.
So what I mean by promoter is the Hill equation, the ascending Hill equation. And what I mean by inhibitor is the descending Hill equation. So nothing goes to A, which means A is created at a constant rate K1, but A promotes itself, so promoter. A is a promoter, hence Hill equation like this.
Why don't you draw the little diagram first? Replicate it from the A promotes A promotes B, B inhibits A. So we have that to reference. Okay, great. Okay, and so now, so you wrote this so far. Do
No.
people remember the process to convert an activator to a Hill function? Elmer, is there something missing here? Okay. What else did we say there had to be?
So I made a decision to multiply both, which means the inhibitor dominates.
No, but just what you have. Why don't we do B first, the way I suggested? Because there's only one signal coming into B, so there's no issue about competition. Okay. Okay. So somebody else, Alex or William, what's missing from what Pedro wrote?
I'm okay. Well, I know what it is, plus B.
Right. So there better be a basal rate of transcription. So there's got to be a B in front of everything. Okay, that's fine. So that to me looks reasonable. Is that reasonable for people?
So I just when you would you not have to flip now your Hill function and turn like we did with the K, taking K into the then in the nominator.
Well,
Or
if we look at our diagram, B is activated by A. That's the only signal coming into B. So there's only one signal coming in for B.
But B is deactivating A, so A should. So there, it's more about.
Right. So for
When
A,
B is high, then A should be low. Not like.
right. So now we have to decide what to do with A. So that's why I said write B first, because it's simpler, because there's only one signal. For B, you have to figure out how do you combine the two signals. Right, there we go. Plus B. There we go. Good. So now you have to make a decision about how to if A is turned on, so it's trying to activate itself, and B is turned on, so it's trying to turn A off. How do they interact? And they could be an and, they could be an or. If they're an or, they could be different kinds of or. Here you've got inhibition dominating, as Pedro says. And in general, this is thought to be true in most systems. If you have activators tend to work as ors. Not always, but often. Inhibitors tend to work as ands. If you have any inhibitor, it turns everything off. And that means that multiplication is the natural thing to do. And so this is the circuit that I would write. And so I think that it's not immediately obvious how to do this. It's something you need practice, but I think Pedro's line of reasoning is sensible, which is if the inhibition is an or, it doesn't do anything, right? If B is really turned on, you want A turned off, no matter what. And the moment you say that, you're talking about an and, because the inhibitor dominates. If the inhibitor doesn't dominate, it doesn't do anything. And so I think that this is a good place to stop. I see Ibrahim had to leave. But I thank you, Pedro, for being willing to work this out on the screen. And thank you, William and Elmer, for being willing to comment on it. And so next time, we'll come back and we'll really work these through. And I promise you next time we finally will get to the phase diagrams. that Ibrahim had shown a little bit of today in his presentation. And again, these were in the homework, and so if people will try to take a stab at doing them, I think it'll be instructive for people. In the case of the homework, as I say, I gave you the equations written out, so you didn't have to do the derivation from the diagram. But if you're going to be in the business, it's really important to learn how to look at the diagram and write equations that are credible. They're not going to be the only ones. They may not be the right ones, but you want to be able to say, here's a circuit. Given that circuit, what's a reasonable first hypothesis about what the equations could be? And as I say, Elmer pointed out that he found a software package that did this automatically. The software package doesn't know anything we don't know. It's just applying exactly the rules I've described. And wherever it sees inhibitor, it plugs this equation in. Wherever it sees activator, it plugs this equation in. If it's
But
all
the software package doesn't do that. The software package just takes a Boolean network and turns it into relaxes the Hill function.
right, well, that's basically what we've done. We've taken effectively a network that the network has basically an activator is an OR, and an inhibitor is an AND with an AND not. And so
I see
we're
what you
doing,
mean.
we're
Yeah, I
doing
see what you
exactly
mean.
that. We're doing exactly that.
Yes, I see what you mean. Yeah, okay. Yes, now I see what you mean. Okay, thank you.
So I'm sure the software does more things than that, but
Yeah.
the basic behavior of the software is what we're doing here. And so I think it really is worth going through these exercises to do it by hand, so that we understand what this process is, because this is really the fundamental thing. And it's not taught. It's interesting. Herbert's textbook doesn't go into this very much about, given the diagram, how do I interpret it? But to me, this is one of the more important things that we can do, because in the real biology, we're going to run into the diagrams a lot, and very often we don't know what the functional forms are. And so we have to have a sense of what a first guess is. What's a reasonable hypothesis to start with? We may not get exactly right. We may have to adjust our results based on what we find. But at least to begin with, we have a basic set of hypotheses. Okay, any questions before we break for today?
So if I want another promoter to dominate over B, I would write something like this. For example, C with a plus sign, because then if this is 0, doesn't matter. I still get C promoting A.
Well, you'd have to draw the diagram. So you'd want a line coming into A that was an activator coming from C. Is that what you want?
Yes, but then here in the decision, I say that this inhibitor shuts this promoter down, but not this one. This one stays available.
Yeah, so this is why I'm saying when you have multiple signals, you can have complex interactions.
Mm-hmm.
So the problem with this is that then the value of A will get to be outside of the range of 0 to 1. Because if they're both on, you'll be turning it on too much. So this one is a little bit more complicated. You basically have, in this case, you basically would have to do, I actually have to think about the way to implement the specific one that you want. You would have an OR between C and A and B.
Yeah, like.
So you would have to have an OR function, and OR, right? You want C. You need an OR though.
Oh yeah.
Yeah, that's what you want. And so then you have to you do is you would write C or X using either competitive and or non-competitive or, and then X you would expand as A and B.
Oh yeah, I see. Yeah.
And so effectively what you'd have then would be you'd actually then multiply A times C and then put that in. So it would be you'd
But
get
by B, you need a not because of you have to turn the B, right? Because it's a blocking.
yeah. So this one is actually tricky. I'd have to I'm to be honest, I'd have to play with this. There are a couple of ways I could write it. I've never done this particular one. Whereas if you have C behaving equally with A and B, I know how to write it. But if you're telling me that you want C to dominate, I have to think about it more. A and B by itself is easy. You've written it correctly with the product. But now if I want to OR it, I have to think more carefully about how I'm going to do that OR. Just adding it onto the end won't work because it doesn't stay within the range that we've wanted.
Yes, I see. Interesting.
And so what I have to do is refactor the Hill function. And it's not trivial to do it. I think probably Herbert and enzyme kinetics may do that one, but it's not one that I have on the top of my head.
Is there a this linear algebra comes to my mind because you have these multiple components acting on each other. Is there a formalism that uses linear algebra? Like I'm not talking about the solving the system of ODEs. I'm talking specifically about solving the interactions between the inhibitors and promoters.
You mean trying to write a functional form that does what you want?
Yeah.
That's an interesting question, and I'll be upfront. I don't know the answer to that. It's interesting to me that in all the years I've taught this course, nobody ever asked that question, and so I do not know the answer. Well, I guess for today, Pedro has the last word. He's brought up a fascinating problem, and I don't have an answer for it. I do have examples where we do put in that extra signal, but not in the way you're doing it. And so you've come up with a particular approach that I don't know. As I said, when you have multiple signals, integrating them is non-trivial. And we're going to tend to, in class, avoid trying to deal with signal situations where we don't know how to do it. But you'll run into that in reality pretty often.